Yes, so hello and welcome student for today's talk. And this is our course MA 425 Topology. And today we have lecture number 14. Okay. Yeah, so today we are going to discuss a very interesting topic. So, and this is called quotient topology. Now, before going to the formal definition of quotient topology, so we can have some nice examples and why it is important, how it's needed. Okay, so let me discuss with you about something called torus. Okay, I hope okay, so what is a torus? Torus is a mathematical term, so you have seen these torus in real life. For example, the tube of a any car, cycle, anything. So, have you seen the shape? Okay, this is this kind of shape, right? And then it's a tube. Or you can see the donut. These are example of torus. Okay, now how this kind of surface made of? Okay, so you can start with a rectangular, say for example, rectangular. What is that? Rectangular paper. Okay, and then what do? You just paste this side with this side first. Okay, and then you can understand that you will have kind of cylinder, right? It becomes a cylinder. So what you are doing, you are just identifying these points to the corresponding points here, right? These 2 points identification. Okay, this kind of you are doing what should I say? Kind of you're defining a equivalent class where this point and these points are in the same class. This same points. Other than that, which are not a boundary point, they are singleton class. Okay, so after making this thing become a cylinder, right? And then so this above side becomes kind of a circle, right? So this side becomes a circle. This kind of okay. After this transformation, this is become. You can think that this is become kind of cylinder, right? Okay. Now what do? You just do the same thing with these two circles also. So you bend it and paste this circle to this circle, and then that becomes nothing but torus. Okay. So this is the process from rectangular shape to cylinder to torus, right? So that means you are giving a map where the original space you're doing something with respect to some map, so that you're getting a new space. Okay, and there are relation between the open sets here, how it look like open set here. Okay, open set here. Okay, this is one example, and one more example I just want to tell you. So this is also very interesting example. This is called Mobius strips. This is Mobius strip. Okay. So what you do? Again, you start with a this rectangular paper. Okay, and now here what we will do here, we will do again this identification. You will identify these points with these points. Okay, but in little bit differently. Instead of taking the direct identification, we will twist it by 180 degree. Okay, so if we twist it by 180 degree, then what happens? Then this point will this corner will come here, and this corner will identify this corner, and this point like this, and this corner will identify this corner, right? Now if we do this kind of thing, then you will have a surface, and this is a very very interesting surface. This surface is called the Mobius strip, and this surface has an advantage or whatever disadvantage, whatever you say, that this surface has only one side. So maybe in my next online lecture somewhere I will discuss this thing. Okay, so or live classes I will discuss this. Okay, so so these kind of surfaces are called Mobius strips, and then you can obviously you can play many things with this Mobius strip. You can try to cut it from the middle and check that it becomes again a Mobius strip, but there are more number of twists. Initially I started with a 180-degree twist, right? Then if you do this thing, then there will be more number of twists. But if you don't cut from the middle, if you cut from some other place, it will be very interesting, amazing. You try to do that, it's homework. Find out, make a Mobius strip and try to find out what happens if you cut from middle, if you cut from say 1/3 distance, or middle, or 1/4 distance, something like that. Cut it through. Okay, so this will give you a nice surface, and that are also very interesting objects. Okay, so by this motivation we will define properly what do you mean by Gaussian map and Gaussian space. So I obviously I can define Gaussian space first, but my goal is to first define a Gaussian map and say that actually the Gaussian space are actually coming from the Gaussian map. Okay, so let us go to the definition of a Gaussian space. Okay, so suppose you have two topological spaces. Okay, it is given that x tau and y tau y, two topological spaces is given, and you have a map also given from this to this. Okay, such that, so this is a map such that with this property that u belongs to tau of y if and only if the inverse image of fiber of u belongs to tau of x. Okay, so you have a map, and you have the map has this property that whenever something is open inside y, the inverse image is also open inside x, and vice versa. Okay, then this P is called obviously I am also assuming surjective map. Okay, yeah, so P is surjective. Okay, this is a symbol of surjective map, two arrows. Okay, P is called the Gaussian map. Gaussian map. Okay, so what does that mean? That means P is a surjective map such that in P satisfies this property that whenever you have an open set in this y, it is open if and only if the P image is open inside x. So so what does that mean? That means you can find kind of one correspondence, right? One correspondence between that. Okay, and obviously when you talk about open sets, then you can also write down this definition with respect to closed set. For example, we know that so you start with a set which is closed set in y, then obviously okay, so for example let B be a closed set in y, then obviously y minus b is open, and you can talk about that P inverse of that, and this will be open. Okay, so this is you can write down that x minus P inverse of b, right? So that means P inverse of b is, so if the map is Gaussian map, if this is open, then this is open, and hence P inverse of b is closed, right? So what does that mean? That means instead of open, you can talk about close also, that if a points maps of the set is closed if and only the image is closed, right? Okay, Okay, so that one-to-one correspondence between the open sets, and then these kind of maps are called a quotient map. Okay, and obviously this is one definition, and you can obviously define. I will give you many examples, but for example, let me start with one example first. The basic example you can just the trivial example is homeomorphisms or open maps. Okay, sorry, homeomorphisms are quotient maps. Okay, homeomorphism. This is trivial, right? So you know that the homeomorphism is also subjective, and okay, so I think here I should write down, but this is subjective. P is subjective onto map. Okay, homeomorphism obviously subjective, and satisfy the condition. It is one-to-one correspondence between the open set, right? Quotient maps. This is simple things. And then the example I have given you, the map that carries these rectangles to the cylinder is a quotient map, right? Just check it. This is a quotient map. Okay, this is obviously surjective map. There is not a problem. And not only that, you see that how this pre-image look like. Okay, suppose these two attached to this line. So this line is a closed set inside the surface topology of R2 or R3, whatever you choose. Okay, and then the pre-image will be union of these and these. Okay, and you see that this is also closed inside this. Okay, so this is one example, and then obviously you can go from here to that torus. Okay, after adding, suppose you are adding this thing to here, suppose. Okay, these are all example of quotient maps. Okay, now now we can have an alternating definition. So alternative. Okay, so this definition is sometimes useful to calculate whether some maps are quotient maps or not. Okay, for example, to prove something is not quotient map, this definition will be more helpful. So so let me define. There is something called saturated subset of a set. Okay, so so we say that we say a subset of subset, for example, A of X is saturated with respect to that map P. Okay, if A is equal to P inverse of some set. Okay, this is a full fiber. This is a fiber of something. P inverse of C for some C belongs to Y. Okay, so if E is a full kind of full pre-image of a thing, so that's called the fiber of a subset of Y, then we call this is a then this we call this is a saturated set. Okay, so so what does that mean? That means quotient maps are those maps which send the saturated subset open set to open set and saturated closed set to closed set. In addition, it is continuous. Obviously, it has to be continuous because full bus of open set is open set, right? So it's continuous, and not only that, it is also sending saturated open set to open set and sending saturated closed set to closed set. Okay, so okay, so thus a quotient map Gaussian maps is a continuous map, continuous onto map, continuous onto map which sends saturated open sets to open sets and obviously similarly saturated closed set to close set to close sets. Okay, so this is full pre-image, and this full pre-image, what about the things? So they should satisfy the similar kind of property also. So obviously from this definition you can easily understood that if it is an open map, then also this is continuous. Open maps are always obviously subjective. You need to assume they are also what is that? Okay, so some more example. So example number 3. So continuous onto open maps. Open maps are obviously what is that? Gaussian map. Okay, Gaussian map. This is okay to everyone. Because if it is open maps, then it will send every open set to open set, and hence it also sends saturated open set to open set, because saturated open set is also open set, right? It sends that also. But if it is not to prove something is not a Gaussian map, you need to prove that there exists a saturated open set whose image is not open. Then you are done. Okay. So maybe I can give an example. So so there are lots of categories. For example, let me write down these projection maps. Okay, say x cross y to x, projection on first coordinate, and you are sending x y to x. Okay, now you see that first of all this map is onto map, right? So you check it. You check that property that projections. Okay, so let me write down by the name pi. That is better. Pi 1. This is pi 1 actually. That pi 1 is onto obviously, right? And pi 1 is continuous also, right? Now if you prove this is open map, then you are done. And then continuous onto an open map, then must be Gaussian map, right? This is the open map. So the answer is yes, it's open map. Why? Because pi 1 is open. Okay, because if you choose any basic open sets inside x cross y, so it will have the from u cross v, right? And if you take the image of this, that will be u, which is open in x, right? So that means that it's open map, right? So thus this projections maps are projects maps are Gaussian map. Gaussian maps. Okay, so whenever you have this kind of projection map, it has to be open map. Now if you Gaussian map. Now if you little bit change it, then you see what happened. For example, now I am not taking full subspace, say R2 to R, but I am taking a very proper subspace. So this is my diagram. Okay. So what is this set? This is A, which is a subset of R2. So this collection of xy belongs to R2 such that x into y equal to 1, right? This is the set. This is clear. So this is the set. The graph is nothing but A. The graph of A is nothing but this, right? So now you see that what kind of set is this? So what kind of set is this? This is obviously closed here, right? So A is closed in R2 with respect to subspace topology. I mean, the product topology of R2, then A will form a subspace. Okay, closed subset, right? So A is not closed, that A is closed in R2, this is obvious. Now question is that what is the image of A with respect to that projection map? The image, what will be the pi 1 of A? And this will be nothing but, other than the point 0, everything is there, r minus 0, right? Okay, so I need to put it back A. So what I do, so I am defining now say A1, which is A, and then union this origin I am adding. Okay, then obviously if I add this thing, then what happens, then you can restrict pi 1 to that A1, and then it will map from this to R, right? And you check that, then check that this restriction map. So let me write down pi 1 restricted on A1. Okay, so this pi 1 restricted to A1 is on 2, obviously, because now 0 also mapped to 0, right? And so if you restrict something, then what kind of map is this? Obviously restriction of continuous is continuous, so we can have this is continuous also. This pi 1 restriction A1 is continuous, but question is it a quotient map? The question is that I just proved that if it is open also, then become quotient, right? But it may not be, converse may not be true. There might be quotient map which is may not be open also, right? But to prove something is not open doesn't matter. To prove something is not quotient map, you need to check that there exists a saturated open set whose image is not saturated, or image is not open, or saturated closed set whose image is not saturated. Okay, whose image is not open, right? So for example, if you choose a singleton points 0 0, what time part is this? So 0 0 is open in A1 with the space subspace topology, right? But the image, what is the image? So but this pi 1 0 0, the image is 0, right? The image of this is 0, right? So the image of this singleton 0 is not open in R, right? So you have saturated, obviously, not only that, these are saturated. So this is also saturated, that singleton, the singleton 0 0 is, so this is equal to actually pi 1 inverse of singleton 0. Okay, so this is full complex fibers of that. Okay, so the singleton 0 0 is a saturated open set in A1 such that image is not open, is not open. So that means what? That means this, if you restrict that, then it will be not a question map. Okay, so then so one can have one more example. You can say that continuous onto and close map. So okay, let me tell you what is close map first. Okay, so let me just first write down that continuous onto closed maps are also they are a question map. Okay, question maps. Okay, so what is a closed map? So let me tell you. So a map is said to be a closed map if image of closed set is closed. Okay, image of closed set is closed. It's like open map. Image of open set is open, image of closed set is open. So here you can say that whenever a map is continuous, open and also closed, instead of open you can have closed also. Then also it can be a continuous map. Okay, sorry, this is also a question map. Okay, so maybe let me give an example. So for example, you have say x is a something like you choose 0 to 1 and then union say 3 to 4. Okay, and your y is, for example, 1 to 3. Okay, this is your y, and then you are defining a map, say p from x to y by p of x equal to, okay, let me write down properly. P of x will be equal to x plus 1. Okay, if x belongs to this first term, so 0 1, and otherwise it is x minus 1 if x belongs to this 3 to 4. Okay, now you see that obviously this map is an onto map, right? Because I mean, this is onto map, we can easily check, right? There's nothing to prove. So thus P is onto, this is first property, and P is continuous because you just use Pesting lemma. Pesting lemma tells you that if you have map which is continuous on two closed subset or open subset, doesn't matter, and on the intersection if they are same. For example, you see that so inside the, okay, so I mean you don't have to prove here anything here, obviously. So so this is same on that points where on so 3 and 1 this is having same image, right? 44 and 1, 3 equal to 1. Yeah, at 1 the image is 2, at 3 is image is 2, so this is same. So this is kind of continuous map, right? So this is obvious also. So P is continuous. You can obviously prove by the proper definition that open sets, pull back open set continuous. Okay, and now I will show that this is it is closed map. So closed map means what? So whenever you have a closed subset here, it will be inside the closed subset of that, and that is also kind of obvious because closed subset of X are nothing. Since these are both are under subspace topology. Okay, these are, so when I'm saying this is subspace topology of R. If I'm not saying anything, these are subspace of R. So that means with respect to subspace topology. Okay, So how the closed set look like inside X? So this will be a closed subset of R intersection X, right? So kind of a closed subset will be kind of a finite union of closed sets, right? Closed interval, you can say that. Okay. Similarly, Y is also same thing. And now just check that this is P is a closed map also, and thus P is quotient map. Okay. So this is an example that you can have both kind of quotient map which is open or closed, but there are examples where P is neither open nor closed also. Maybe I will tell you later. Okay, so everything all the kinds of this kind of maps can exist. Okay, now let me tell you that with respect to these kind of definition, you can define a topology on that space Y. Okay, so now proper definition, let us come. Okay, for example, suppose you have this P from X to Y, and you know that P is a quotient map. Quotient map. Okay. I mean. Okay. So no, I should not say quotient map. But I mean, I need to define a topology for which it becomes quotient map. Okay. So how do I define? Obviously, I can what I said initially, that I can define by partition, but that I will come later. But let me first define it by this. So this is any surjective map. We say onto map. Then there exists a topology. Then there exists a topology on Y such that P becomes a so X is topological space is given, whatever. Okay, and Y is any set is given. Then I can define a topology on Y such that P becomes a quotient map. Quotient map with respect to obviously this topology, with respect to this topology. So how do I define the topology? So this is given, X, tau X is given, and Y, I don't know what is tau Y, so I will define this tau Y. So how do I define tau Y? So tau Y is collection of all subset of Y such that this P inverse of U belongs to tau of X. Okay, this is my definition. Now you check that this becomes a topology first of all, and this topology will make okay, so this topology will make the row P is a quotient maps. Okay, so how do you check this is a topology? Now obviously phi will be equal to nothing but P inverse phi. Similarly X is nothing but P inverse of Y, right? So this implies that phi and Y belongs to tau Y, right? and for arbitrary union and finite intersection, what do you need? So you choose, let say u alpha belongs to lambda is arbitrary collection of open sets in Y. I mean, so arbitrary collection of open set Y means is inside tau Y, and then you can easily check that P inverse of union u alpha belongs to lambda, and this is nothing but is union of P inverse of this. Okay. Okay, and hence, so this is open in X, so this union is open in X, so this belongs to inside tau of X, and hence this union of u alpha is tau of Y, so union of u alpha belongs to tau of Y. Similarly, the finite intersection also, so this intersection I equal to 1 to n ui, P inverse of that, this is nothing but intersection of P inverse of ui I equal to 1 to n, this belongs to tau of X, and hence the intersection of y belongs to tau of Y. Okay, so this forms, so the way you define the tau forms a topology, and this topology is called this tau Y forms a topology on Y such that obviously you can easily check now that P is a quotient map, because first of all P is onto and is exactly open sets are same, right? The way I am defining, such that P is a quotient map. Okay. So this tau Y is called the quotient topology, Quotion, quotient topology on Y. Okay, is that okay? So this is the topology which is coming from topology of the domain. So we have a map from the domain, it is coming. Okay. Formally, I will define it such a way that this becomes quotient topology. I will define another way, but let me just give an example. And okay, so another example. I don't know how many example these numbers. So I think 6, 7, whatever. So you have a map, say P from X to, you have 3 points, 1, 2, 3. Okay. Or ABC, whatever you write down, better to write down ABC, otherwise you will confuse. So ABC, and how do I map? Sending the maps. I'm sending. So for example, this is real line. This is 0 is there. Whenever it is less than 0, I'm sending this portion to A, and then greater than 0, I'm sending this is to B, and the 0 going to send it to C. 3 points. So what does that mean? That means P of X is A if X less than 0, is B if X greater than 0, is C if X equal to 0. Okay. Now it's obvious. You can check that this map obviously generate the quotient topology. Okay, that topology is what is the topology that induced by this map P. So this is, let me just write down, this is my Y, this set. Okay, and X is R, real line. Okay, so then what is tau Y? Tau Y induced by the P, obviously phi and Y, full thing is there. And what are the open sets here? So open sets are those whose pre-image is open. Now singleton A is open because the pre-image is that open race. So singleton A is open. Similarly, singleton pre-image of singleton B is also open here, right? That open race. So singleton B is also open. Okay, and obviously hence the union obviously open. A B is also open. But what about singleton C? Singleton C is not open because the pre-image of singleton C is singleton point which is not open. So this is the topology. So this is the topology which is actually induced by that P, and this is the quotient topology, is the quotient topology on Y such that that P, the map P, is a quotient map, right? Now I am asking you a simple question, that so whatever we have discussed so far, that I have given an example where it is a open map, where it is a closed map, right? And obviously where both open, both closed, because for example, homeomorphisms are both open and closed, right? But here is an example where it is neither open nor closed. Can you check whether it is open map or not, or closed map or not? You can check that this is not open nor closed map. Why it is not open map? So you need to find out the open set whose image is not open inside Y. Okay, and similarly it is not closed also, that you need to find out the closed set whose image is not closed. Okay, so for example, why it is not open? Why? So question number is this P open or is P closed? Okay, I'm asking both questions. Okay, to prove that something is not open, what you need to prove? You need to prove that you have open set. For example, -1, 2, +1. This is open inside R, okay, which is X. Now what is the image with respect to this set? This set, what is the image of this? What is the image of this? Check it. Or what is the image of say open set? Okay. Okay, so yeah, so you check it why it is not open, not closed map. Okay, this is, I'm just giving some example, but you have to check it. What is the reason that it is okay? So here obviously this is you can easily find out that because you have element less than 0, so A will be there and 0 will map to B. C, that C is there, but that is open, right? But can you find out the open set or R which is whose image is not open inside here? Okay, and can you find out the open set whose image is close to whose image is not close here? Okay, for example, say okay, so -infinity to 0, this is a closed set inside R. What is the image here? No, image is a closed set here. Okay, so okay, so what do you need to find out? So can you find out something which is not closed? So which is not closed inside singleton ABC means what? That so you can find out the image is singleton, obviously. So image is singleton, say B, singleton B can be. So this is not closed, is open, right? Can you find out whose image is this? One question, and vice versa, I can find out. Okay. So either you can do it, take the example that arbitrary union of open set open and arbitrary intersection of closed is closed. With the help of that, can you find out that? Okay, find it. Okay. So now, so with the help of all those things, so we can now formally tell that what is how we can define a quotient space properly, or maybe we can wait for the next day. Okay, so maybe let us stop here because it's a new idea you are just learning. So maybe I will define next day properly that how you can just let me just define it, and then I will stop it. Maybe that is better. Okay. So you have a topological space X and you have a partition. So suppose X is given, so kind of this, and you have some partition. Okay, partition means proper subset of this such that neither of two is intersection. The union is full thing, right? And so maybe this X star be a partition on X. So what does that mean? That means X star is a collection of subset of X such that no two subsets has intersections. They empty intersections, and union is equal to X. Okay, and then you can define the map P from X to X stars. And how do you defining? So you are defining the map which carries, for example, so X star is something say x1, x2, something say xn. Okay, where xi is a subset of X. Okay, so xi is a subset of X. And then what you are doing, you're defining the map small x size. You choose an element that will be one of the partitions inside one of the subset, right? And then you are defining this xi to that x size. Obviously this is a map and this is onto map, right? So if you have this map which is of this form, then the topology, you can define topology on X star induced by this map. Okay, and this is the quotient topology, and this space, this X star one can write down this X hat, the equivalent. See, whenever you have a partition, that will form equivalent relation, right? Because you are telling that the points here are in the same classes. Here are same classes, So these are the point kind of equivalent classes, right? So you can write down this by this tilde, where tilde that x tilde y, if x and y are in same partition. Is that okay? So this space is also, this is the actual example of quotient space where the quotient maps are that the original maps which is sending an element to that class. Okay, so this is one of example on the way where you can define the quotient space. How to find out the quotient space. And now recall that our original example, the torus. In torus, what we have? In torus, we first do this. So we identify this to this, and this quotient space is also called identification space because we are identifying all the elements, the singleton element. So like this line and this line I'm identifying, and then I'm identifying. After that, it becomes this kind of cylinder with this is the line where it's joining these two things, and then I identifying these two things. Okay, so what does that mean? That means after everything, when it becomes torus, then so for example, this is the place where it meet. Then these 2 points, 4 points, they become a single points here somewhere. Okay, and these two lines, they becomes a single line here, somewhere here, somewhere here. Okay, and these two lines become a single line. So this, okay, and other than that, inside all the inside interpoint, they have singleton class. Okay, so this is one of the example of torus. Maybe I will write down proper some more example in next class with more properties. Okay, so today I am just finishing my lecture here. Okay.